Okay, welcome to E123 Digital Signal Processing, Lecture 27. Woo! Transform analysis of LTI systems. So we're kind of switching gear towards the last topic of the class. Okay, so this is chapter 5 in the book. We moved from filter design, and you'll see now that it's very, very relevant. We talked about linear phase, for example, in the filter design. What does actually mean linear phase? You know, it was just a filter that has a pure delay, right? But we'll see what actually those things mean. What's a frequency response, amplitude response, phase response? How do we analyze systems and how we make sure, for example, systems have a minimum delay, a maximum delay, uniform delay, and so on and so forth. Okay? So this will be the last topic of the class. So we're marching rapidly towards the end. Truth is, it's not rapidly, no more rapider than before, but it just feels that way. Okay, and you'll see. You just get sunk more and more with work. That's how this class is designed. You don't notice in the beginning, and then it's just like you just sucked in. That's it. And then you just feel so that you have to make your friends also take this class too. So, right? And that's how the cycle continues. All right. Continuing with this, I have a few announcements. To make the compressed sensing homework worthwhile, we'll use this score to replace your worst homework and your worst lab score. Okay? So, just to make it worthwhile. All right? There you go. So you should do it. Projects, again, start thinking about it. 1 week about it work. Groups to minimum. I'll talk about projects next week. Yeah. Yeah, whatever. Not today. Not this. Material. Okay, material. Yeah. Now you got me out of, yeah, okay. Groups 2 minimum, 3 possible, depending on the scope of the project. There'll be a default project based on Lab 6. You can have a custom project. I'm hoping, personally, that you'll be using the software-defined radios or the radios or both in these projects. You could do really, really cool stuff, building a really nice systems. If you want to do something else, I'll be open for suggestions, but my openness you'll feel my resistance. So you have to be really convincing if you want to do something else. Okay? But as long as it's aligned with the class, I'll be okay. And if it's a serious and creative project, yes. When is the compressed sensing? Yeah, you can. Well, when do you want it? It's optional. So, Frank will post on Piazza because he's gonna decide. Okay, so Lab 5. All it's meant really is to taste radio waves and stuff and connect. But really, is also to test the interface that we, this audio interface. The ESG folks, Winthrop, actually put a lot of work in designing something that it's nice and that doesn't break, hopefully doesn't break as we had last year. But the idea is that this is a USB connection. You've got a USB hub, and then there's an audio. Basically, it's a digital to analog converter and an analog to digital converter. Okay. Both in. It's a audio card, right? It samples at 44.1 kilohertz. Okay, so that's the sampling rate. You can figure out actually what is the Nyquist and so on and so forth, right? So, but that's what it does. And then there's also a USB to serial device, which is meant really to control the push to talk. So now, by issuing a command to this, you can basically issue a command to the radio to transmit or to stop transmitting. That's better than last year where we just used voice activation. So only whenever you had a sound, then the radio would activate itself. but this is much faster. You can switch between on and off. You've got audio going into a ground loop isolator. Basically, it's an audio transformer. Just puts, if you think about it, is a bandpass filter, okay, analog bandpass filter that doesn't pass DC. Okay, so if you have some voltage across, between here and the computer, and you don't want to create these ground loops that will burn some of your circuitry. So this is basically a high pass for that. So it only passes audio. Okay, high bandpass, not high. Well, yeah, it's a high pass, but also it will be a low pass because it's just inductors. Okay, so then all these ferrite cores, what they do is basically try to eliminate any current that flows on top on the shield of the cables. When you transmit, that can be induced on the shield, and so these are low-pass filters, okay, analog low-pass filters that try to dissipate the energy that high-frequency energy that goes on these cables from the outside. Okay, and that will help you minimize interference. But the idea also that you take the radio away, especially from these two devices. Okay, they're very sensitive. They might just reset. Okay, so take this as far as possible as you can. Okay, so this is the interface. It's really, really nice. Just one connection to the radio, and that's it. Some possible problems that could occur. Do you see a Windows user star? Okay, there's going to be a COM port for the USB 2 serial device, and I don't know what the number is. So you have to figure out what its number. And then you just need to change it. You see, it's changed. Exclamation point, exclamation point, exclamation point. Dash, 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 dash. Try to put your attention there. For Macs, we figured that out. It was relatively easy. I'm sorry. But I don't know how Windows assigns COM ports. Okay, COM 1, 2, 3, 4. If COM 1 is occupied, then it'll move it to COM 2, and then I don't know. Okay, so you figure out which COM port is. This function here, what it does, it basically on the serial line, it puts either a 0 or a 1. A 1 keys the radio, a 0 unkeys the radio. 1 keys the radio, 0 unkeys. So here for 10 times, it will turn on, turn off, the radio. Okay, it will transmit, stop transmitting. So when you do this, you need to identify yourself before that, right? Okay, when you're starting to do all these experiments. And do that on the experimental channels that we gave you on the band plan. Okay. The other thing that can go wrong is the audio device number. So the USB device has a number because you're going to play audio through the speakers of your laptop as well as play audio through the USB device, these two. So you need to tell the radio which device does what. We came up with a function that with high probability is successful. But I'm sure high probability is like, 2%, right? But there's like 50 people, okay? So that's at least one of you will have a problem, at least. So on average. But not at least, on average. Yes, so this could also not work. So you have to, that's another one to debug. Okay. One thing you will be doing after going through and making sure that you can listen, through the music that sound that is played on the radio goes into the computer and then it played in real time. So just to make sure that capturing and play works. Okay, so you're going to go through this. You're going to transmit and turn it on, turn it off, and then what you're going to do is connect the SDR, and you're going to be transmitting a chirp through the radio, okay, through the audio interface of the radio, and it's going to be FM modulated by the radio, picked up by the SDR, sampled, right, and then and then you get the samples. Now this is the histogram of the. It's not a histogram; it's a spectrogram. It's a spectrogram of whatever was played. Okay, the FM, the chirp, FM modulated chirp. And you see that for some reason it increases amplitude, and it really shouldn't do. If you play a chirp has a constant amplitude. Okay? And the reason that it changes, its width is because there is a filter, and the filter on the audio interface of the radio, inside the radio, has a bandpass filter. So low frequencies are not passed, high frequencies are not passed, and there is some roll-off. Okay? So you can kind of almost visualize what would be the amplitude response of that filter, because the amount of deviation that you've got in FM is related to the amplitude. If I play constant amplitude, I should have seen a constant bandwidth coming out of FM. But that's not what's happening. So you can almost see the filter. But then after you demodulate, FM demodulate, you get the chirp. This is a spectrogram of the demodulated FM. Similarly that you did in, basically listening to the radio in previous labs. And you see that, first of all, there's a few things that are interesting. The intensity changes versus frequency, and that kind of makes sense if you have a filter. But also there's some nonlinearity, so you see a second harmonic here. And as you reach higher frequencies, there's kind of aliasing. And basically these are nonlinearities, and that's what happens. But it's actually a pretty nice one. You might see it even worse if you keep the antenna of the SDR connected and you're transmitting from here. It's going to completely overload your SDR, and you see way more nonlinearities because of that. So take the antenna off, put the transmitter on low power, okay? And the gain of the SDR, set it to be low, because they're so close that you're definitely going to pick it up. Then you're going to look at the amplitude response, and you're going to see that it has really this is the bandpass filter shape of the audio interface. Okay, so that's kind of cool. All right, once you do this, and this really should not take you that long, we gave you a dictionary of Morse code. You're going to write a function that converts text to Morse code and then transmits and receives it using the SDR. And this is, I think it's KK6MRI, something like this. But basically, you'll be transmitting your call sign. So this is kind of a way to actually identify yourself now for any experiments that you're going to do. You're just going to run this function, whatever your call sign. You're going to say test on it, testing, and then that's good. You're good with that. So then you can just test, and you satisfy the FCC rules. You don't need to speak now. Okay? So that's enough. Okay, so this should be fun to do. You'll hear some yeah, and which is considered a digital mode, by the way. Any questions? So I hope you don't have a lot of trouble with, connection and stuff. But this is what happens when you have to deal with real equipment. Okay, it's always what happens. And so part of, I think, the added value in this class is that we give you the feeling of this pain as an engineer, that you have to deal with real systems and actually mitigate with them and identifying what's wrong. For example, this overloading of the SDR. I mean, I have to say, when I started working with the software-defined radios, and I didn't have so much experience actually working with radios before, and it's like I couldn't. Yeah, well, what's going on? I mean, it samples it, right? It has the A to D. It should be good, right? Get samples and everything should be fine. Well, gain control and things like this are really important. Overloading of systems, all this plays into the whole system of the whole. So I think what we're trying to do here is to give you kind of this complete picture. Okay, so you come up to the real world ready. You don't seem impressed, but when you get a job, maybe you'll be like, oh yeah, I remember that. Yeah. Okay. What else? Yeah, that's pretty much it. Wait a second. Yes. All right. Okay. So one thing I didn't talk about before is we talked about FIRs, and we talked about optimal filter FIR design. We didn't really talk about IIRs. And frankly, I don't want to talk about IRs. Okay? Yeah, you can spend a lot of time explaining and doing all this, but I have to say that the time you're going to spend actually designing IR filters beyond, taking putting inputs to functions, I don't know. Most of you probably not, and those that will need to design like the specialized IRs are more than welcome to read the chapter in the book. But I just want to give you some ideas of what are these. So continuous IR design was really advanced, so that's why one of the reasons that people used IRs in the beginning. They used all these results from continuous time and translated it to discrete time. The nice thing about continuous time IRs is that they have these closed form designs. And so they were very easy to use and easy to control the magnitude, but not really so easy to control the phase. Okay? With FIR, it's really easy to control both. Okay? Now, there's different types that people have come up with for these closed forms. The Butterworth filter is monotonic, has no ripple whatsoever. You've probably seen this in 120, right? You've seen Butterworth filters? Have you? Okay. Well, they're basically monotonic without ripple. Okay? But they're not very selective. Chebyshev, there's two types of them. One, type 1 has a passband ripple and monotonic in the stopband, and type 2 has a stopband ripple and is monotonic in the passband. And of course, there's the elliptic one, which is ripples in both passband and stopband. Okay? How do you design? Keynote not responding. Force quit. Sorry about that. So how do you design? You design an IIR. You discretize by one of the many techniques that people came up with. If you have the transfer function, basically the Laplace transform of the filter, you want to convert that into the Z transform somehow. Okay, so from H sub C to S, the continuous filter, into something that is discrete. Okay, so if you remember the complex plane of the Laplace transform, you want to transform that into the complex plane of the Z transform. Okay? If for the Laplace transform you had the imaginary line, right, that separates between both sides of the complex plane, now that line will become a circle. Okay? So a filter must satisfy a few things: that the imaginary axis is mapped to the unit circle. Okay, so whatever inside the unit circle, like if you have poles, they have to be inside the unit circle to be stable. In the continuous domain, they have to be on the negative side, right, of the plane. So you want to maintain the stability. So any stability here should result in a stability here, in terms of the conversion of these filters. And there's kind of two methods that people come up with. People also always teach this one first, because it's really easy to understand, but it's never used. What you try to do is to try to match the impulse responses of the two filters. If you have the impulse response in the continuous time, you want to try to match as best as possible the discrete impulse response, okay, to the continuous one. And the other one is what's called a bilinear transformation. So you have a mapping of this complex plane such that whatever is on the left side of the complex plane, okay, the negative part will be mapped into the inside of the unit circle. Okay, so you apply some transformation to the variables that does that. Okay, and whatever is on the right-hand side will be outside of the unit circle. And this is called a bilinear transformation, and there's rules how to do this effectively. So by designing a filter in the continuous domain, that will give you a certain frequency response. Then what you want that after the mapping, you have a filter that matches your criteria. Okay? So this is kind of the idea. But I have to say that today, even with convex optimization tools, you are able to design an optimal IIR filter as well. Okay? So there's other tools that you could perhaps use, and there's papers in the literature that describe how to design them. Again, you can use something that is optimal to your application. You don't have to go through these transformations. Okay? And that really depends on the application of how complex really you want, or what are the criteria for the system that you're really interested in, how much you're going to spend effort designing a filter. I mean, it's often, if the filter is 2 or 3% difference than your criteria, if your criteria for the design of the filter are not strong, right? They're not going to make a big impact on the result, then maybe it's not worth it. But in some application, if you really want to attenuate something to, 100 dB, well, maybe then you have to be really careful. Okay. Any questions? Okay. I didn't really show you how to design it, right? But, for example, if you want to design a Butterworth filter, what you go is use NumPy, or you can use MATLAB, and it's called butter. The function is called butter. Right? Or Chebby, right? That's the Chebyshev filter, and so on and so forth. And that will give you the coefficients. All right. Now I want to talk about, here's a slide that I actually had to move before that you didn't. Where's my slide? Yes, this one. So what we're going to be talking about during the next few lectures is about the case of linear difference equations. Okay? This is a class of problems a class of systems that are relatively easy to analyze, and with enough order can approximate any other system. Okay? But they are parameterized to this particular form, which makes it easy to deal with. Okay? So if you look at any rational numbers, I mean, you could approximate any irrational number, or at least put it between any two rational numbers, right? So this is kind of the same idea here, is that you can design very complex systems using this simplified parameterization, okay, of linear difference equations. In a linear difference equation, the output depends on the current input or some past inputs as well, but also on some past outputs. Okay? So you have coefficients both to past inputs and present, as well as past outputs. Okay? An example, y of n equals x of n plus 0.1 y of n minus 1. Okay? If you think about this is an infinite impulse response, okay? Because enough that you have, basically it will be something that would decay over time, but it would be infinite, right? If you put an impulse through the system, because of this feedback, it will last forever, although decay relatively rapidly. Okay? But it is an IIR system because of the feedback of the past input, the past output. Now, when you describe these type of systems, these are in fact you can write them as the ratio between two polynomials, okay, in the Z transform. So anything here is really delay in the inputs. Delay is z to the power of how much it's delayed. So, and you have on the bottom is delayed of the outputs, delays of the outputs with coefficients, and then it's again z to the power of whatever delay. So it's really nice. This has a really nice transfer function, which is a polynomial with z on the top and a polynomial with z on the bottom. The coefficients on the top, all the b's correspond to the coefficients of that are multiplying the inputs, and the a's are the coefficients that are multiplying the outputs. So you've got these two polynomials, and you can decompose these polynomials to the roots. Okay, for example, just by multiplying, just a polynomial decomposition, right? All right. So now we want to think about what is a magnitude response of this kind of a system, okay, of this difference equation. And we're going to look at the magnitude of the transfer function, basically the magnitude of the frequency response. And if you write down, what is the transfer function and evaluate it on the unit circle, which is exactly what the frequency response means, right? The frequency response is the evaluation of the Z transform on the unit circle. And now we're going to look at the magnitude. Is really just the multiplication of all the magnitudes of the roots. The zeros, basically the roots of the upper polynomial corresponding to what's called the zeros, and divided by the magnitude of the roots of the denominator, which are the poles. Okay, so if you just consider one pole system, okay, where the coefficient, the pole is at dk. Okay? So it's a one-pole system. And we'd like to figure out what is the magnitude response of this single pole system. Then if we look at the magnitude of the numerator, which is 1 minus dk, that's the position of the pole, e minus j omega, that's the magnitude frequency response. What effectively you see is that if you transform this, you can basically just transform this into e to the plus j omega minus dk, right? You multiply by e to the plus j omega on both sides. E to the plus j omega has an amplitude 1, so it's okay to multiply both sides. It doesn't change the magnitude, so it's equivalent to this. And so this is basically just the distance between the point on the unit circle that you're looking at to find what is the frequency response, and how far is it in, what is the geometrical distance, right? The Euclidean distance between the point on the unit circle corresponding to that frequency that we're looking at and the pole. And of course, it's going to be inversely proportional because it's going to be in the denominator. Okay? So here it's the closest point, so we're going to have the highest amplitude. And as we move on the unit circle, we're getting further away from the pole. Then the distance is going to grow. 1 over something that grows, the amplitude diminishes. Okay? This is the shortest distance. 1 over something that's short is amplified. So is this a high pass or a low pass? It's a low pass. Why it's a low pass? Because where are the amplified frequencies? Are low frequencies, and the higher frequencies, which are on the other side, they are going to have a lower amplitude. Okay? But basically, it's just the inverse of the Euclidean distance, okay, to a pole. What about a zero? It is the Euclidean distance to the zero. Okay? All right. So, for example, if you have this particular system, again, now it's a zero. You have a 0 at -1, and then a pole at somewhere here, I think at 0.9. Okay, a pole at 0.9 and a 0 at -1. Then now, what is going to be the magnitude response? The magnitude response is going to be the Euclidean distance between the point on the unit circle, which we want to figure out what the magnitude frequency response is. So it's this distance divided by this distance. Okay? This distance divided by this distance. And so in that case, the result that you're going to get are, if you start from here, that's going to be this distance divided by this distance, and then so on and so forth till you get to the point here where there's really no distance to the 0. So frequency is 1 in this case because of the 0.05, and then it's just going to drop down when you get to the pi. Okay, so this is a low pass system. Okay, So it's really easy to look at the magnitude response just from a geometrical point of view to figure out, how far I am from any zeros. I'm going to multiply all these distances together and then divide by how far I am from all the poles. Okay? All right. So now if I have, so now it's kind of, you can think of, certain order systems that you can design filters using them. Okay? Here's an example of a simple low-pass filter that I can parameterize by the fact that I'm putting a 0 and I'm putting a pole, one pole and one 0. And I can parameterize them by an alpha. So one parameter, okay? A parameter alpha is how far the pole is going to be along the, how far is going to be, basically how far this is going to be, whether it's going to be in the middle or it's going to be all the way to the end. Okay, so this will be the alpha parameter. Okay, where I'm going to put this pole. Based on where I'm going to put this pole, that's going to decide where my cutoff frequency is going to be. Okay, and so the response for this is going to always look like that. Okay, but based on alpha, that's going to kind of smooth this curve a little bit to the left, smooth this curve a little bit to the right. And as it turns out, that the point where I'm going to have a magnitude which is 1 over square root of 2, then that point is going to be at omega c, and I can parameterize alpha based on this to 1 minus sine omega c divided by cosine omega c. Okay? So if I want to design now a low-pass filter with one pole and 1 0, I'm going to look at this equation and I'm going to say, okay, I want to put I want to make my cutoff frequency to be omega c. That determines alpha, and then I just plug it into this equation, and then I have my low-pass filter. Okay? Very, very simple. Okay? This is an IIR filter, of course, because it has a pole. And it has one pole and it has 1 0. That's it. Okay? If I want to make a high pass, then all I need to do is switch. You see, here it's 1 minus alpha. I'm going to switch it to 1 plus alpha. Okay? That's all I did. This is exactly the same, but if I do that, then this is what I get. Basically, an inverse of that system. Now my 0 is on the other side, and my pole is on. Again, the 0 and pole location are just flipped. Okay? So this is a very simple 3 dB cutoff frequency, just one pole, 1 0 system. What if I want to make a bandpass? Okay, or a band stop? I cannot do that using this kind of a system. Okay, I need more than one pole, more than 1 0 in order to do this. Okay, so then if I want to implement a simple band stop or a notch, what's called a notch filter, then I can again parameterize it in a very particular way. So the transfer function is going to look something like this. So now it's a second order polynomial on the top. It's a second order polynomial on the bottom. So I'm going to have 2 zeros and 2 poles. Okay. Why do I have, by the way, to have 2? Yeah, because I want it to be a real system. If it was just only 1, then it would have been complex. Okay? In order to have real coefficients, I need to have always 2. Okay? I need to filter both the positive frequencies and the negative frequencies. Okay? Remember that actually in some of the labs, you did make a complex filter, and there's a reason to make a complex filter, right? To do one-sided. Okay? So sometimes that's useful. So bear that in mind as well. Okay, so what I do, if you actually think of what is this, what is this polynomial on the top? 1 minus 2 beta z minus 1 plus so on and so forth. If you actually, write it down, if you make beta to be cosine omega 0, this is the parameterization. What you're going to get is you're going to get a filter which has a notch exactly at omega 0 frequency, okay, because you're going to be placing the 0 on the unit circle. Okay, so that's going to go down. And you're going to control by how sharp that filter is going to be by changing alpha. Alpha will move the poles as close as possible to the zeros, basically making, when they actually exactly on top of each other, they cancel. Okay? But as long as they're not, that means that frequency over here is always going to be nulled. Okay? So if you think about the parameterization, the closer it gets, then the curve becomes sharper and sharper and sharper. And that's your ability to control of which frequencies is going to pass and which frequency are going to be stopped. Okay? So omega 0 is really the inverse cosine of this beta parameter. So now you've got, again, you want to design the second order system, band stop filter. What you need to do is, okay, I have a certain criteria of what frequency I want to eliminate. That determines beta. And then I want to figure out what is my 3 dB cutoff. Okay? And that is going to determine alpha. Okay? And that's pretty much it in this type of a design. Okay? So as alpha goes to 1, what you'll get is that the poles approach 0, and then at the end you're going to get basically cancellation, and so the transfer function is just going to be 1 because they're going to cancel. Okay, that's the point here. What about bandpass? Bandpass you can parameterize in a different way. Okay, so if a band stop, we'd like to put the 0 and the zeros on the unit circle at the frequency that we want to cancel. In a bandpass, we'd like to put the poles as close as possible to that frequency, so to the middle of the frequency that we want to pass, because they're going to amplify. Now, why are they called poles and zeros? Do you know? It's like a tent, pretty much. If you look at the amplitude of the Z transform in space, right? Whenever you have a pole, it's like taking a pole of a tent and pulling it up. And when you have a zero, it's like you take a peg and you peg it into the ground. Okay, that's really how that thing looks like. And the amplitude frequency response is really what is the height of the tent on the unit circle. Okay, and we're trying to control it by basically using these poles and pegs. Okay, moving that amplitude around for different frequencies that we are interested in. So of course, if we want a band pass filter, we don't want to pass DC. We don't want to pass the highest frequency, right? We want to pass somewhere in between. So we're going to put the zeros here on both sides. Okay, so high frequency is attenuated, canceled, and then the lowest frequency is canceled. And then we're going to put the pole somewhere that will control our 3 dB effectively cutoff frequency. Okay, so you parameterize this in this particular way. Again, inverse cosine of beta will determine omega 0, and alpha will determine how much, how tall my pole is going to be. Okay, if I put it really close to the unit circle, then it's going to amplify. Okay, one thing that we didn't talk about this in this class is that if you actually realize the system and you realize it discretely, you have to eventually quantize the coefficient. Right? You're going to have quantization of the coefficients of that filter. And you have to realize that when you design it, you want to make sure at least that after quantization, your system doesn't become unstable. Okay? That can happen. Whenever you quantize something, it changes the coefficient, and then those can change the system. You want the quantization not to affect the system so much. Okay? So you need to take that into account. But this is something that we're not going to cover in the class. But bear in mind that everything that you do digitally is effectively quantized. Okay? So if you get it really, really close to the unit circle, let's say 0.999999, and you can't represent it using floats or int16 or something like this, then that's going to be different, and that might actually result in a non-stable system or a system that doesn't do what exactly you want. Okay, so this is amplitude response. Amplitude response, it's relatively trivial to understand. the height of the pole, it passes, doesn't pass. This is typical parameterization that help you kind of design something. For example, this is, it's a way to design a second order, IIR filter, okay, using this parameterization. But what I really want to talk about that is something that gets people confused is phase. Now, I love phase. I love phase. Phase is great. Phase is the best thing ever. Really. It's actually where all the information often is stored. Okay? Amplitude, most audio signals have the same amplitude. Okay? Most audio signals have the same amplitude. Like if you look at a spectrum, the magnitude spectrum of speech, looks the same for everybody, almost. Right? Deep voices maybe will move a little bit to the left. High voices will move a little bit to the right. But they kind of look the same. The phase of the frequency response holds the information of where things are. And where things are, this is the information that often we need. Okay, let's say I'm going to say the ABC. It's really important that I say them in the right order. Because if they're flipped and changed, they're going to have exactly the same magnitude response when I say it. If I say it, one after the other, right? But if I flip them, that's going to make a mess, especially in a word, right? So, yes, all the letters are going to pass, but the information is going to be different. The order really makes a big difference. And the phase controls these delays. And so it's really important to understand what it is and what does it mean. So now I want to spend, I've got only 8 minutes. I'm going to start spending some time, the next 8 minutes, talking about phase response. And we're going to continue talking about phase response in a group delay next time. Before that, any questions? Before we move on.
You were saying that, say, you should say ABC and DAC. If you do the transform, they're going to have different phase?
Yes.
Okay.
Oh, yes. Actually, let's say my signal starts now. Okay? Now it's my recording, right? N equals 0, T equals 0 is now. Okay? And let's stop. And then I compute the Fourier transform, and I get something, and it's probably going to be, a few harmonics corresponding to the Right? All right. What about now? My measurement starts now. It's going to have a different phase because these are delays with respect to each other. Right? It's actually, the difference is going to be mostly linear phase because it's just a pure delay of this. Whenever we delay something in time, it's a linear phase in the frequency domain. Right? So all the information is really just going to be stored in the phase. Okay, when I say it. Okay. So now let's talk about phase response. Phase is it's just an amazing thing, phase. It really is. But it's really all about delays. Okay? And it comes out in all sorts of systems. Optics comes, of course, in MRI. MRI is like we live phase, we breathe phase. Okay? It comes actually, like head counseling phone, headphones, for example. What you do is you try to cancel the phase of signals such that they cancel to 0. Okay? Because you have signals that are, positive pressure. You want to, at the same time, apply something that will create a negative pressure that will cancel that positive pressure. Right? Antennas, you can, by changing the phase of whatever you stimulate, you can actually steer antennas. And your routers, when they have these 3 antennas, they do that. They change the phase between them so you get most of the signal to where you are rather than anywhere else. So that helps improving your signal. So phase is, it appears everywhere. All right. So a phase response. if you look at this particular frequency response, h eta j omega equals to E minus j omega n sub d. Okay, what's the magnitude response? Boring, right? It's an all pass. It passes everything, right? This is an all pass system. It passes everything. But it does something. What does it do? Well, it will delay everything. By how much? If this is an integer, it will delay it by n sub d samples. Okay? So really, there is information there, but all the information for this particular system lies in the phase. Everything is passed, but the fact that I have what's called a linear phase. And why is it called a linear phase? It's called the linear phase because if we look at the phase of that sequence, of the frequency response, it's going to be a linear function. Okay? If I'm going to look at the argument, which is, by the way, if we're going to talk about the small ARG, that's the unwrapped phase, so it doesn't have these pi jumps. Okay? If it's capital, then it's going to have the pi jumps, the 2 pi jumps. Okay? But if you look at the unwrapped phase of this system, it is a linear function of the frequency, okay, of the angular frequency. A linear function. That means that a linear function of the phase creates a pure delay of the output signal, of the input signal. Okay? That's why it is desirable sometimes. Now, what happens when you have something a little bit more complex? Okay? To really characterize a general phase response, we often look at what it's called a group delay. Okay? A group delay is the negative derivative with respect to the frequency of the phase response, okay, of the unwrapped phase. Okay, so if you look at the unwrapped phase, you take a derivative of it, and then the negative of that, that's the group delay. So if I have a particular phase response, okay, this is a phase response of a system. If I look at the slope at a particular point, or the inverse of that slope, that will be what's called my group delay. Now, why is that even interesting? Why am I looking at this? What's the group delay of this linear phase? What's the group delay? No. It's the derivative of this, the negative derivative of this. What's the negative derivative with respect to omega? ND. How much delay I get? ND. The group delay is really the delay in this case. Okay? So what we're really interested to see is really, you have a linear phase, but the coefficient of that linear phase, that is really our delay. So this is why we're interested in this quantity. Okay? In the case where it's nonlinear, why is it interesting? Well, it's interesting because if you think about this, let's say I put a narrow band pulse into that system. And that narrow band only has support around omega 1. It doesn't see the rest of the frequency response, right? It only is concentrated, it's a narrow pulse. It's a pulse that has, frequencies only around omega 1, right? Just like if you could think about almost a pure frequency, but like that's windowed, okay? So it's concentrated all around here. It doesn't see this, it doesn't see this, it doesn't see this, it doesn't see anything. All it sees is it sees this part of the phase response. And when it sees a narrow part of the phase response, really what it sees, approximately, is just its slope. It sees a linear phase, right? And what's that part? It's really just the slope here. And so that's going to tell us how this narrow band pulse is going to be delayed by. Does this make sense? If then I transmitted a narrowband pulse over here, that doesn't have any delay. It's just going to go through. So now, if I transmitted these two pulses at the same time, after that system, one pulse is going to be behind the other one, which is called dispersion. Okay? Even though they might all pass through the system, different frequencies are going to be delayed a different amount. And we find how these frequencies are delayed by looking at the group delay. Here is an example, and I'm going to finish. Here's the group delay. Sorry, this is the frequency response of a particular system. I'm going to put these two pulses. This one is a pulse around omega 1. This is a pulse around omega 2. I'm going to put these pulses into the system. Omega 2 will have very little delay, right? Because if you look at this, the slope is really small. The one around omega 1 is going to have a lot of delay. And it's basically going to pass the pulse with omega 2 and end up ahead of it. Okay? Now, is this real? Is this real? Are you real? This is not possible, right? Not possible. Well, think about a prism. What does a prism do? Okay? If you think about this, white light, all frequencies come in. And what comes out? Colors. Why? Because different frequencies have different delays or different velocities. Okay, inside the glass. Now, although everything passes, because of the different velocities, they'll come out with different delays, and so we're going to get separation of these colors. It happens in fiber optics. You send a pulse. Let's say we want to do on-off keying on fiber optics with white light. What's going to happen with a fiber optic when I transmit white light through it? It's going to have dispersion. Different frequencies are going to be dispersed. And so I'm going to send a pulse, a white pulse, short one. And then at the end, I'm going to start getting colors one after the other coming out. The pulse is going to spread out because of that. Okay? So that is kind of the effect. Now, even though there's no loss of energy, there is dispersion because of the phase response. All right? We'll talk about more next time. See you on Friday.